Hello everyone, and welcome back. In our last two lectures, we are going to cover as much thermal physics as we possibly can. So, this is Thermal Physics Overview, Part 1. One thing that we have not talked about in the previous lectures is how temperature affects objects, how it affects systems. So, what we're going to be doing in the next two lectures is talking about that, how temperature and heat affect different objects. We have a good qualitative sense of temperature. We can pick something up and, well, this is very hard to pick up. We can pick something up and say, oh, this feels colder than this or something like that, so this is at a lower temperature. Although even the perception of temperature, these things have both been sitting out at room temperature for a long time, so we would expect them to be at the same temperature as the room temperature, although they feel different temperatures. So we've got to be a little bit careful about even our perceptions of what temperature is. So how do we go about measuring this thing? What is temperature? It turns out that temperature is actually a measure of how much internal kinetic energy something has. We've talked about kinetic energy before, that if something is moving, it's got some kinetic energy that's equal to 1/2 mv squared, 1/2 times its mass times its velocity squared. But objects can also have an internal kinetic energy. So we know that material objects are made up of atoms and molecules and things like that. Well, these things are moving around. If it's a solid, they pretty much stay in their same relative position, but they can move around to some extent, even around their positions. If it's a liquid or gas, these can move around much more around each other. So the atoms and molecules themselves can have some internal kinetic energy, which we don't necessarily see because of the motions being very small and it's not actually changing the shape of the object. The temperature is then kind of a measure of how much internal kinetic potential energy there are between these atoms and molecules. So how do we measure what temperature is? Well, what we need to do is find some kind of property of a system or of a material that changes with the temperature. This is called a thermometric property. In other words, it's a property that we can use to measure the the temperature of the object. So what this is a property of the object that changes with the temperature. And then we use whatever the value of this property is to assign a temperature to the object. One very, very simple quantity that changes with temperature, well, it's not always very simple, but some is simple for some materials, is the volume of that material. So, for example, if we take a, say, a reservoir of some liquid, so here's some liquid in here, up to some point on the in the tube. So there's a liquid here, reservoir, and there's a tube here. If we heat this liquid up, the liquid expands, and the height of this liquid then goes up. We can then use the height of the liquid and assign a temperature to it. And as long as the temperature changes are not too much, the change in the liquid is linearly related to the temperature, and so we can subdivide this into equal subdivisions, and this allows us to define a temperature scale. This was done by Fahrenheit, who used, so he made a thermometer, used the coldest day in winter to define his lowest temperature, which he defined as 0 degrees on his temperature scale, and his body temperature as being 100 degrees on the temperature scale. And so we end up with these two extremes, and then he subdivided them into 100 degrees of Fahrenheit, well, I don't know, 100 degrees, and then used that for the temperature scale. It then turned out that water froze at about 32 degrees, and it boiled at about 212 degrees, but these definitions of 0 and 100 degrees, the coldest day in winter and his body temperature, are not very consistent. So to develop a new, more consistent temperature scale, some constant physical quantities were used. the freezing point of water and the boiling point of water. And then the freezing point of water, it depends on the pressure and things like that. And so an even more precise point, or what's called the triple point of water, was used to define. So for us, we've got this other temperature scale, we'll refer to it as the Celsius temperature scale, that goes from 0 degrees at the freezing point of water. Now, it actually turns out that the triple point is defined as 0.01 degrees Celsius, but for us, typically we'll be keeping to 3 sig figs, so we'll just say 0 degrees Celsius. And then water boils at 100 degrees Celsius. So, because these are the two most commonly used temperature scales in ordinary everyday life, we'll have a conversion between them. It turns out that the temperature in Celsius is equal to, I want to make sure I get my factors right here, 5/9 times the temperature in Fahrenheit minus 32 degrees. And just inverting this, we have the temperature in Fahrenheit is equal to 9/5 times the temperature in centigrade plus 32 degrees Fahrenheit. Okay, so we can go back and forth from Celsius to centigrade. There is one more temperature scale that is very, very important that will be used later on some, and that is the Kelvin temperature scale. If temperatures measure the amount of internal kinetic energy of the system, what happens if the internal kinetic energy is 0, is at its lowest possible amount? Well, that's how the Kelvin temperature scale is defined. So 0 Kelvin is when the internal kinetic energy is as absolutely low as it possibly can be. All the energy is taken out of the system, and that's 0 Kelvin. It is related to the centigrade Celsius temperature scale in that the temperature in Kelvin is equal to the temperature in Celsius plus 273. Now there's some decimals here, but the 3 sig figs, we'll just leave it at that. 273 Kelvin. So that means that 0 Celsius is 273 Kelvin, 100 Celsius is 373 Kelvin, and the absolute lowest temperature, where 0 Kelvin, would be negative 273 degrees Celsius. So absolute 0 is negative 273 degrees Celsius. Now this is such an important number that for my students, I would really expect you to remember that. So remember that 273 Kelvin, and remember how this fits in here, because it is a very, very important number. Okay, so what other kinds of properties do systems change with temperature? What can we look at? Well, let's take a look at some of those. So, as I mentioned, the volume of objects increase as the temperature increases. This is not always true. There are some materials that actually expand as they cool down. For example, when water gets close to its freezing point and forms ice, it actually expands. So not everything follows exactly this strictly speaking, but many things do. So I'd like to do a little demonstration about something here. So here I have a little metal ball, and this ball will just fit through this little ring. So the ball fits through there. Now what I'm going to do is I'm going to heat up the ball, and I'm going to do that with a little torch here. There we go. Okay, so ball goes through easily. So I'm going to heat this up here. And after it heats up a little bit, get it up at the point, what we notice is that it won't come out of the ring anymore. However, if I cool it down in some ice, cool it down in the ice, and then it comes right back out. So what happens is the ball expands as we heat it up, and what we're going to take a look at is exactly how much some things expand. Let's imagine that we have a rod here of some initial length L0, so at some initial temperature the length of the rod is L0. As we heat it up, and let's imagine that we increase the temperature, let's say by some amount delta T. So delta T is the amount that the temperature increases, and in general, all temperatures that we use for most of these things will be in the Celsius temperature scale. When it needs to be something else, I'll mention that specifically. So if I don't mention it, you may assume that the temperatures that we're talking about are in Celsius. So let's assume we increase the temperature of the rod by some amount delta T. So the whole rod is going to expand. Not only the length will increase, but the width and the depth, they'll all increase. Let's look at just one dimension of increase. So what's the change in the length? We're not going to worry about the width or the depth, just for now. So let's assume that the rod expands by some length delta L. So how big is delta L going to be? Well, what's going to affect delta L? Well, we expect that the larger the temperature change, the bigger the rod will expand, the larger delta L will be, and that is the case. And as long as I mentioned before, as long as we don't increase the temperature too much, the bigger delta T, the larger delta L, and they will be proportional to each other. So delta L will be linearly related to delta T. What else? Well, it turns out that it's also dependent on the initial length of the rod. This kind of makes sense because if we had another rod of the same length, this part would increase by delta L, this part would increase by delta L, so the overall increase of the length would be 2 times this much, 2 delta L. So if we double the initial length of the rod, with the same temperature change, we would expect twice the increase in length. So that kind of makes sense. The increase in length delta L, we then expect to be proportional to L naught. Anything else? Well, there are other things, external pressure, things like that, but we will assume that the external pressure is constant. We'll just assume we're in ordinary, everyday atmospheric pressure, so to speak. But what else it depends on is the material. Different materials expand different amounts. So we'll put the dependence on the material in the front with a constant that we'll call alpha. And alpha is the coefficient of linear expansion. So linear expansion because we're only looking at the expansion in one line in one dimension. So we get this very simple relationship. Delta L equals alpha L naught delta T. Well, let's stick some numbers in here. Let's imagine that we have, say, a 1 kilometer long length of railroad track. So we've got a steel track that's 1 kilometer long. And we're going to look at how much this expands from, say, a cold day in the winter to a hot day in the summer. How much is it going to expand? Well, there are railroad tracks all over the place. How much do you think? If you just think about it, how much do you think it's going to expand? You know, small amount, large amount? What do you think? Well, let's stick the numbers in and find out. So, we've got an initial length of 1 kilometer or 1,000 meters. Let's say the initial temperature, the cold temperature, is a freezing day, 32 degrees Fahrenheit or 0 degrees Celsius. Hot day in the summer, 100 degrees Fahrenheit, that would be about 38 degrees Celsius. The linear expansion coefficient for steel is 1.2 times 10 to the minus 5 inverse degrees Celsius. We'll see how those units work out in just a second. So what's the increase in length? Well, delta L will be 1.2 times 10 to the minus 5th inverse degrees Celsius, alpha. L naught, 1 times 10 to the 3 meters. Delta T, 38 minus 0, 38 degrees centigrade. Notice here that we've got degrees Celsius inverse and degrees Celsius. They cancel out, which will leave us units of length in meters. And so we get delta L is equal to, let me get the number here right, 0.456 meters. 0.456 meters. This is almost half a meter long. So that is quite a bit. That is a big expansion. Well, there's no way that just a solid railroad track would be able to take that much expansion without warping and bending itself. So, long pieces of metal that are used in construction and things like that must have some way to be able to expand and contract over different temperatures, so that they don't damage the structure that they're making. For example, if you ever drive across a bridge, you might notice something that looks like this. There's a joint in the bridge that looks something like this, where you've got one section of the bridge metal over here and the other section over here. So you've got these fingers that kind of fit into each other like this, and what it allows to happen is it allows the bridge to expand and contract into itself like this without causing a distortion in the bridge like this. So allowing the metal to move back and forth uninhibited to some extent keeps it from making something a dangerous situation that it would be impossible to drive over. Okay, very good. So here's how things expand in one dimension. What about in 3 dimensions? Well, it's related. The amount that it expands in 3 dimensions is related to the amount that expands in 1 dimension. Let's take a look at that.